Welcome into the next video in my series on essential skill number 1 for AP Chemistry, dimensional analysis and mole conversions. So we've been talking about some different types of stoichiometry problems, and in this video I'm going to introduce another application of stoichiometry called solution stoichiometry. So a solution in chemistry is a homogeneous mixture. So it's going to contain a solvent, which is whatever substance is present in the greatest quantity, and then at least one solute. Most of the solutions that we will deal with, particularly when we're doing solution stoichiometry, will only have one solute, but in theory, you could have several different solutes. And most of the solutions we deal with, particularly in solution stoichiometry, will be aqueous solutions, meaning the solvent is water. Okay, so molarity is a measure of the concentration of a solute in a solution and can be used to convert between the moles of that solute and the volume of the solution in liters. So this is the equation for molarity, moles of our solute over the liters of the solution. So that provides us a conversion factor between moles and liters, moles of solute and liters of solution. So if we have a 0.50 molar solution of a particular solute, that means that there are 0.5 moles of that solute per 1 liter, or for every 1 liter of the solution. Or in other words, 0.5 moles of that solute is stoichiometrically equivalent to 1 liter of solution. So we can use that as a conversion factor in a stoichiometry problem. So let's look at this example. How many grams of aluminum hydroxide are produced when 50 milliliters of 0.2 molar aluminum nitrate reacts with 100 milliliters of 0.4 molar potassium hydroxide? So this is a stoichiometry problem. Okay, so for the most part, most of the steps are going to be the same steps that we do for a standard stoichiometry problem, but we're introducing molarity as well, which sort of gives us a new wrinkle on these types of problems. So as always with stoichiometry, we're going to start by writing out a balanced chemical equation for the reaction that takes place. All right, so the first step is to write out our balanced chemical equation. So we have aluminum nitrate reacting with potassium hydroxide. So aluminum nitrate, that is AlNO3,3. And I'm going to write states of matter as well. You don't really have to do this problem, but a lot of times in AP chemistry you'll be expected to, so I'm going to do that just to show you. So typically when we have molarity, it's going to be for an aqueous solution, unless it's a gas. This example is, it's not maybe explicitly stated, but these are aqueous solutions of aluminum nitrate and potassium hydroxide. These are also both soluble in water, which means that their state will be aqueous as long as there is water present, which again, it's not explicitly stated, but it's kind of implied in a problem like this. So state of matter here is going to be aqueous, and then potassium hydroxide is KOH, also aqueous. And then our products are also going to be aqueous as well, as long as they're soluble in water, because this is all taking place in water. So our products are going to be double replacement, so aluminum hydroxide, which is AlOH3, which is actually not soluble if you check the solubility rules of ionic compounds in water. This is not soluble, so that would be a solid. And then our other product is going to be potassium nitrate, KNO3. That is soluble, so that's going to be aqueous. Anything with potassium or nitrate, as long as it has either of these ions, is always soluble, along with a few other ions that are always soluble. These are two of the key ones. So then we have to balance the equation with coefficients. So we have 3 nitrates here, so put a 3 in front of the KNO3. And then we have 3 Ks now, also 3 hydroxides. So put a 3 in front of the KOH. So that's our balanced equation. Now, typically with stoichiometry problems, we have to get into moles if we're not already given the moles of one of our things, one of our substances. So that's what we're going to do here, but the way that we're going to do it here is using molarity and using the volumes that they give us, okay? And you can either do that using just the molarity formula, or you can set that up as like a dimensional analysis conversion, which is the way that I'm going to show it, okay? And this is also going to be like a limiting reactant problem here because they give us the starting amount of both reactants. So remember from my limiting reactant video, when they do that, we have to essentially do 2 stoichiometry calculations, 1 for each. Next step is we are going to use the molarity. So molarity is moles over liters, moles of solute over liters of solution. So we're going to use the molarity and the volume to get into moles, okay? And you could do that just using this equation. I'm going to show you how to do it using like dimensional analysis conversions. And then we're going to have to do it for both reactants because they give us the amount of both reactants. So it's like a limiting reactant problem where we have to do 2 calculations, 1 for each. So I'm going to start with the aluminum nitrate with the 50 milliliters. And first, before I can use the molarity, I need my volume to be in liters. So milliliters on the bottom, liters on top, and there are 1,000 milliliters in 1 liter. You don't have to explicitly write out this step if you don't want to, but you do have to make sure that you do divide by 1,000 to get into liters. And then one way of using the molarity is how I'm about to show you here. It tells you how many moles there are per 1 liter. So in 1 liter of aluminum nitrate solution, this aluminum nitrate solution, there are 0.2 moles of aluminum nitrate. That's what a molarity of 0.2 means, okay? And then, so this would give us the moles of aluminum nitrate. And then let's do the same thing for the potassium hydroxide. So we have 100 milliliters of that. Divide by 1,000 to convert to liters. And then multiply by its molarity, 0.4 moles of KOH per liter. Okay, and if we stop here, this would give us the moles of each. You could go ahead and calculate those. We're gonna have to keep going though, so I'm not necessarily gonna stop and calculate those. I'm just gonna continue my stoichiometry from here. So, but that's the first thing we have to do is get into moles of each before we can sort of proceed with sort of the regular stoichiometry. And so then once we find the moles of each reactant using the molarity, it just becomes a regular stoichiometry problem from there to ultimately end up in grams of aluminum hydroxide. And once again, we're going to have to do that calculation for both reactants because this is a limiting reactant problem. And then whichever one generates less of the aluminum hydroxide, that's the answer that we're going to go with. So once we're in moles of our reactant, we can convert to moles of our desired product, which is aluminum hydroxide. So I'm going to put moles of aluminum hydroxide on top, and then moles of aluminum nitrate on the bottom. And those both have coefficients of 1. And then here, I'm also going to put moles of aluminum hydroxide on top, but moles of potassium hydroxide on the bottom to cancel that out. And Again, this is a 1, but potassium hydroxide is a 3. Okay, so we're not done yet, but I'm going to go ahead and stop my calculation here and go ahead and calculate the moles of aluminum hydroxide that we get for each of them. A, because I'm running out of room, but there is also another reason why this is a good place to sort of take a quick break, do a calculation, and then we'll finish after that. So for the top one, we should do 50 times 0.2 divided by 1,000, and that gives us 0.01. Okay, technically 3 sig figs, so I'll leave those zeros at the end. Moles of aluminum hydroxide. And then this one, 100 times 0.4 divided by 1,000, and then divided by 3. That is going to give us 0.0133 moles of aluminum hydroxide. Okay, so now comparing, so this is how many moles of aluminum hydroxide would be produced if all of the aluminum nitrate reacts. This is how many moles of aluminum hydroxide will be produced if all of the potassium hydroxide reacts. Well, so we have enough potassium hydroxide to produce 0.0133 moles of aluminum hydroxide, but we don't have enough aluminum nitrate to produce that much. We only have enough aluminum nitrate to produce 0.010 moles of aluminum hydroxide. So the smaller value, that's how much you're actually going to get. This is review from limiting reactants, okay? Because again, once we've done this first part to get into moles, everything else from here on is really just review of problems we've done so far. The only real new thing is using molarity to get into moles. So now I'm just kind of reviewing the limiting reactant process. So once you get into the same unit of the same product, you just pick the smaller value, okay? And so this value is not going to be our answer even for the moles. Again, that tells us how many moles the potassium hydroxide could produce, but we see that the potassium hydroxide is going to be our excess reactant. So this answer it doesn't really have a meaning in this context. So this is going to be really the correct amount, but it wants us to do it in grams. So now we can just take that and convert it to grams by multiplying by the molar mass of aluminum hydroxide, which is 78.044004. How do I know that? Well, because I already had this is take 2 of this video, so that's how I know. So these cancel, and we get 0.780 grams of aluminum hydroxide. Okay, and again, you could have converted both of these all the way to grams and then just compared the numbers. That would have been perfectly fine. You still would have gotten this for the top one. You would have gotten something bigger for the bottom one. So this would have been your correct answer. But it actually does kind of save you a step if you stop at moles, because then you only have to convert the smaller one to grams. You don't have to bother converting the larger one to grams. So that was some review with limiting reactants. Hopefully you remembered all that. And then hopefully also this new stuff with molarity and how to incorporate that into a stoichiometry calculation makes sense as well. So to summarize this video and the last few videos in this series, we have this stoichiometry flowchart, okay? And so let's start in the middle of it. The key here is the moles, okay? The moles are kind of always at the heart of this stoichiometry flowchart. Everything flows through them. So the only way to convert between one substance and another substance is to do the mole-to-mole conversion from the coefficients from the balanced equation. But then we have all these different ways of going into or out of moles. Probably most commonly it's going to be with grams using the molar mass. But we can also convert into and out of particles using Avogadro's numbers, and we can convert into and out of liters. We've now seen 2 ways to do it. Okay, we saw how to do it using the 22.4 liters per mole, but we can only use that if it's a gas at standard temperature and pressure. Okay, now we have another way of converting moles to liters if we know the molarity of the solutes. So if you can you don't necessarily need to memorize this flow chart exactly, but kind of just be thinking along those lines. Just sort of, understand that the key is the mole to mole, and then, you know, we could tack on a conversion from some different unit into moles at the beginning and being aware of the different ones that are possible. And then you can tack on a conversion out of moles at the end and being aware of the ways to do that, which are essentially the same as the ways to go into moles, just in reverse.